So, welcome everybody to one of the most hyped talks of today. Duarte Carmo, he's going to present an introduction to Google Earth Engine, exploring geospatial data for machine learning. Thank you so much for coming, Duarte, and
Thanks.
The floor is yours.
Well, I normally have to explain how to pronunciate my name, but that was said perfectly. So yeah. Hi everyone, my name is Duarte. It's a Portuguese name, very well pronounced. I'm a machine learning / software engineer and contractor. I'm originally from Portugal, but I've been based in Copenhagen for the last 7 years. I like running a lot, and I like writing for my blog a lot. In the past, I worked in strategy, product management, like new ventures, management consulting, so I did kind of the rounds. Now what I do is I help companies solve really tough problems, and one of the latest problems I had to try to solve was really related to geospatial data, hence kind of my talk. So today's talk is going to give you a glimpse into the possibilities of geospatial data. It's really that, it's a glimpse, right? I don't have a lot of time, so I will not get into the nitty-gritty, but I'll share my slides after. We'll talk about geospatial data and why it matters. We'll talk a little bit about Google Earth Engine. I'll talk about some examples of machine learning applications that you guys might be interested in. And now for the grains of salt. I am not a geospatial engineer. I'm sure there are some here, but I'm not. I'm also not trying to sell you things. I couldn't care less about if you buy Google Earth Engine or not. I'm just trying to show you how it solved a lot of problems for me. And if you disagree with me, great. I'm so glad. If nobody did, we wouldn't have any interest. So raise your hand, come talk to me after the talk. Would love to discuss. All right. So what the hell do I mean by geospatial data? First of all, so geospatial data for me, it's everything, all data generated from observing our planet in space. So either that's images like RGB bands from the Sentinel-2 satellites, things like temperature from multi to hyperspectral satellites, things like vegetation, like the Normalized Vegetation Index or NDVI, or things like land cover, like is this latitude and longitude a farm, a city, a factory, things like precipitation, like how much rainfall did I get on this particular point up to now. All of those, in my common view, are geospatial data. And it's a super rich source of information, right? I mean, hundreds of satellites, multiple providers like NASA, the EU, amazing derived data sets. So a lot of people that just take this raw data and transform it into something super useful. And it's free. A large portion of it is actually free and open, which is super cool. But yeah, handling it, accessing it can be a real pain. So every satellite is different. Every provider has a different portal where you have to log in and request access. People use different units, different resolutions, potentially a data engineering hell. And I do not like data engineering hells, to be honest. So hence, talking a little bit about Google Earth Engine. So Google Earth Engine solves most pains when accessing and manipulating geospatial data. It has one API, started in JavaScript, which is a bit yicky, and now it has Python for a couple of years. It has unified documentation for most products. So most products, like satellite products, are available in Google Earth Engine. It has a compute platform, so you can actually run computations on their side, not on my side. I usually do not like to run them. And it's free for research purposes. It's paid for commercial applications. And they have a continuously updating catalog of satellite products. All right, some concepts. So we have our planet, right? We have a satellite going around on the left. Every time the satellite goes by, it takes a photo. We create what is this image collection. So it's a collection of images, literally. We can filter by a specific date range on the top, or we can reduce it by a mean, an average, or a standard deviation of those images, and we basically get a single image. We take that image, and that image is just your plain photograph. It's an image composed with a lot of bands. But traditionally, in your photograph, you have RGB. In satellite imagery, we imagine you have up to hundreds of different bands. So Sentinel-2, for example, has RGB, but also B8, B12, B whatevers. It has a multitude of bands. And so, yeah, you can actually select those bands if you're interested in some of them. And while you're browsing through Google Earth Engine and you're seeing all of these different data sets, this is what one of them would look like. This is the land surface temperature data set. It shows you, OK, when is that data set available for? Is it an image collection or an image? And then you see all the tags that help you kind of get an idea that it's an 8 days, so every 8 days you have some information about it. It tells you the resolution, so it's 1 pixel is 1,000 meters, so it's a kilometer by kilometer, or yeah. And then, yeah, you have all of the bands, so the land surface temperature day, the land surface temperature night, you have the details like the units, here's in kelvins. So every page of a data set, you have a multitude of information of how you can actually access it and how to use it, right? For the ignorants like us. All right, so how exactly do we use this type of stuff? So imagine I want EuroSciPy. I define the latitude and the longitude of, I hope, exactly where we are. We define a point, so here's the geometry point from Google Earth Engine. We first start by getting that image collection that I showed you before, and then we process the collection. So we filter out by the dates, here in this case is year to date. We select certain type of bands, so the day temperature band and the night temperature band. We take the mean, we multiply and we subtract because we want to get degrees. And then in the end, you can see we sample that image into the region of the point, and we get basically a dictionary with the average degree temperature during the day in EuroSciPy and the average for the night year to date. OK, now let's talk a little bit about machine learning applications. How does this work? How can we use it? So the first machine learning application is for tabular or time series. So using Google Earth Engine to extract rainfall data as a time series, as an example. And so here we have a data frame, right, of like monsoonal rains or heavy rains or some sort of like problem that was with rain that was too much, and how many people got displaced, if any of these people got displaced, and then you have a date of when this particular phenomena occurred. I don't know if phenomena is a good word, but this particular thing occurred. And then what we can actually do with Google Earth Engine is that we can actually take each date and point where that occurred, and then look at 30-day time periods back, and basically reconstruct the time series of rain that happened before that point. And so here you have basically the first column is 30 days back, the second is 30 days up before that, and before that, and basically you have a time series of rainfall leading up to that monsoon. And what you can actually use this is basically to predict like the likelihood of having a monsoon or in a certain place at a certain time. And I will not delete those nans because I want to make sure that you know that geospatial data is a pain, and you'll have lots of nans where you're not expecting because satellites are not always there when you expect them to be. So those nans are going to stay there to make my PowerPoint slide very ugly. All right, how do we actually get this data? First of all, we compute the time periods for each date and point. So for each date and every point, we actually need to know what those time periods looking back are. Then we need to fetch the image collection, which this gets time series for point in date. We fetch the image collection, we map through the time periods, and we filter out the data. So basically, what we're doing is taking that image collection, looking at all of the keys of our time periods and reducing it. This code looks kind of messy. It's very hard for you to get an idea of what everything the code does in 1 minute, but I'll share my slides and you can kind of read it carefully. So it's 3 functions. It's compute the time periods, fetch the image collection for that point and date, and then merge back to the original data frame. All right. So let's talk a little bit about a computer vision application. So going from coordinates to computer vision applications. So basically, what we see on the left side is the 3 bands, the RGB bands, but they're called in Sentinel-2 terms B4, B2, and B3. And you're actually looking at an image of Basel, really up high in the sky. And then each one of these bands basically is a matrix, 275 by 750 matrix, and every point on that matrix has actually the value of the RGB band, in this case the B4, the B2, and B3 bands. And it's actually a mean of those bands. What you can actually also get is, in the middle, you can actually get the latitude and the longitude for exactly that matrix, so you can map back, right? You can actually know at which point latitudes and longitudes map back to a certain value. And then a classic, right? You can actually like put these three bands, the B4, the B2, and the B3 on top of each other to reproduce the RGB image of actually Basel. And so basically, you can imagine the applications here. You can basically take any area on Earth, as long as the satellite data is available for that area, and then build any type of computer vision application you see fit. So either that is like, okay, looking at how many factories there are in a particular city and how the carbon emissions went around on that city, or perhaps looking at traffic patterns, or perhaps predicting where the nice likelihood of fires are or what happens. Basically, you can apply to this to any sort of like box of latitudes and longitudes. You can get a massive amount of data about it and predict any type of thing you're interested in predicting. And this is really, really powerful, specifically with geospatial data. Now, how does this work? Again, on a very high level, you define a region of interest. So here I define a rectangle that is roughly basal. I get the image collection of the Sentinel-2. I get a specific date. I want to look at only 7 a.m. to 12 a.m. I want to filter by clouds, because that's another big problem that I hate about geospatial data and clouds in general, even though I live in Denmark, is that particularly in Sentinel data and satellite data, you actually have to filter by clouds, because otherwise all you see is a big white thing. We select the bands, we define the scale and add latitudes and longitudes, and we then sample that rectangle in the image that we want. And here in the last part of the code, I'm basically printing out the arrays. And another super cool thing, in my opinion, about geospatial data is that you're not limited to your classical RGB. So in most applications, right, when you think about a convolutional neural network, and you like the input channels are normally like 3, right? So you go in with the R's and the G's and the B's. But basically, you're talking about geospatial data. You actually have many more bands that only RGB. Like I was talking before, like Sentinel-2, for example, might have a total of 11 bands. Some of them your eyes cannot even see. But you can actually leverage them for computer vision applications. So you can actually take those bands and integrate those bands into your like neural network to take advantage of things that, yeah, our eyes cannot see. So you can actually go multi or hyperspectral in some of these cases, what you might not expect to do. Now, tricks and tips to keep in mind when working with geospatial data. This slide was, the title was a work in progress. I was going to call it traumas. Traumas from the past 9 months. So, first of all, it will be painful. If you don't like pain, go do something else. Avoid local loops. So, Google Earth Engine gives you a good capability of like running computations on their site. So, if you're running local loops on your machine, you're probably doing something that you shouldn't be doing. Then, learn functional aggregations. Perhaps a reason why Google Earth Engine started with JavaScript is it has like really functional API. So you need to know your maps, you need to know your reduces, you need to know all that stuff, and your camel casing, even though I don't like it. So better get comfortable with those functional aggregations like the means and the mappings and the lambdas. Get comfortable with those. Then, mixing satellites can be really tricky. Okay, so know exactly how you're mixing them, why you're mixing them. Look at the resolutions. Make sure you're looking at the scales. Know what you're like putting into your soup. Then understand the bands. Here I was talking like B2, B8, B whatever, but really know what each one of those bands mean. Specifically in Sentinel-2 or other satellites that are like Landsat and things that are more used, to really know why you are using a certain band in your like deep learning application, for example. Don't just throw everything in there, please. And then dates matter. Dates matter a lot because there's a big important dimension about geospatial data rather than satellites, that it's the dimension of time. And so satellites are not on top of your city all the time for you to get a live feed of what's happening down. You actually need to know how to aggregate those times in a smart way. And so, yeah, dates matter. Now, closing thoughts. Very cool, Duarte, so what? Well, I mean, there's more and more data every day. Like every time, basically every day that passes, every month that passes, the geospatial data and the data available gets bigger and bigger and bigger. And a cool thing about Google Earth Engine is that you get access to all of this data in a single Python roof, which is pretty nice. And you can actually access this data in a tabular way, get image data from it, get multispectral image data from it. And the community is really great. So you have things like Gmap, which is another Python library that actually has an abstraction on top of Google Earth Engine, so you don't write all of this ugly code that you've seen today. There's a nice podcast called the Mapscaping podcast that you should know. And there's also like a couple of really like good newsletters on the topic and community. I really been enjoying more and more the geospatial community. And then, yeah, a lot of sustainability use cases. So a lot of things are actually related to Earth, like wildfires, predicting like carbon, looking at farms, productivity of crops, like everything that you can actually see from Earth is a potential geospatial application of Google Earth Engine. And the last thought that I want to leave you with, because I'm out of time, is that our planet tells a story, right? Like when we look at MNIST and we look at the 7, a drawing of a 7, like it's a 7. It's a 7 because someone just went there and drew a 7. But in the case of like looking at Earth, and if you look at the picture of like Basel or any place on Earth, it's actually what you're trying to do is, it's a culmination of like years and years of things that happened on that place until it happens. And so the time aspect of all of the history of that point is much more important than just like, hey, snap a picture, predict something. You actually have to look much deeper and really take care into that time variable, because Earth ultimately kind of tells a story. And yeah, that's kind of the idea. Sorry it was so short, but hopefully you enjoyed it. Thanks.
So thank you so much, Duarte, for your talk. We have time for some questions.
Hi. You said that it's free for researchers.
Yeah.
I actually tried it, and after a bit, it said, no, it's not free anymore. You used your stuff, and we don't allow you anymore.
Really?
Yeah.
I've been using it for research purposes for about 8 months. Didn't really happen to me, but maybe I did something wrong.
Yeah, okay.
I don't think I paid. I'm pretty sure I did not.
Yeah, I ended up playing around with some other API that scrapes Google Maps, because then I could use it for free.
Yeah. I mean, I think it's also super worth it, right? But one thing that before getting into all of this kind of data, is that Google Maps, when you zoom in enough, it actually is aerial imagery. It's not really like satellite imagery. And so like it's very different, because if you want to really get granular on like a picture of a street, then the only providers available are paid providers like planet.com and things like that. Yeah. But as soon as you get upper and upper, then it's free. Yeah. Should be free.
Thank you.
Awesome.
Maybe Duarte can help you later.
I will talk to Google, don't worry.
Yeah, so first of all, thank you, really nice talk. You mentioned the bandwidth. I wasn't too sure what you meant there. So you had the B4, B...
Oh yeah,
B3.
okay, yeah, so
is it like different channels from the B?
Yeah, so basically, imagine you have here the image, right? So your typical image is your RGB image, right? So if you look at the bands there, I put the blue, the green, and the red. But in a satellite image, what you actually get is not only the R, G, and B. You actually get many other bands. But there are like multispectral or hyperspectral bands. So they're not called RGB. They're called something else. Yeah. Does that answer your question?
Yeah.
All right, awesome, great.
Good. We have time for, yeah.
Very interesting talk. So I'm a bit new to this field, but I'm very interested. You mentioned you filter the clouds out. Mm-hmm. Is it the procedure supported by the engine, or you have to build something yourself to do it?
No, it's actually supported by them. So let me see here. Okay, so basically, I was telling you that there was a bunch of bands, right? Here, I'm selecting the B4, the B3, and the B2 bands. So I'm selecting the RGB bands. It's there like on the line, it should be like 9 or 10. It's at a dot select B4, B3, B2. And then before that, I'm doing a filter lower than cloudy pixel percentage 20. And so basically, what Sentinel-2 data, I think it's Sentinel-2 in this case. Yeah, Sentinel-2 also adds another band called cloud pixel percentage that you can actually use that band to filter out the image. And so they already give it to you, fortunately. It will be a big pain. Maybe you'll need to manipulate it a bit for certain scenarios, but actually they provide it out of the back. And here, to make this image kind of pretty, I only wanted to see pictures that actually have lower than 20% pixels that are in clouds. So I picked a particularly nice time of the day, otherwise you would not get this pretty image. So, but now you kind of flubbed my trick. Because when you try to do it at home, if you don't filter it by clouds and you just take any time of day, you'll probably get nights, and that will be very black. Yeah, but I'll share the code. You can look at it carefully at home.
Okay, I think we have time for one short question. If not, you can actually talk with Duarte later. Okay.
God damn it.
So, are there some libraries or things that exist to use these multiple different satellite resolution in a nice way?
Sorry, can you repeat your question, please?
Does it exist some library to help you use the different resolutions in an easier way, basically?
So that's the nice thing about Google Earth Engine, is that you don't need an extra library to do it. So let's say you're mixing, like rainfall data, which might be like 250 meters by 250 meter pixels. And you're mixing that with Sentinel-2 data, which is like 10 meter by 10 meter pixels. You can actually upsample or downsample the data so that you can mix those, and you can take, like, let's take the resolution of the Sentinel-2 and then rescale the rainfall data to the Sentinel-2. You can actually do that on Google Earth Engine particularly easily. They have a good docs about it. But you should be aware, right, that it's, for example, if I would put in this particular image, right, the rainfall image, then you would get big squares, right, because each one of them would be 250 meters. So you just need to be aware of what you're doing and what the application is. If you're trying to predict at the city level, that might be fine, but if you're trying to predict on the street, then everything will be the same because it's 250 by 250. Does that answer? So use it. It's super easy. Super easy. Yeah.
All right. Thank you so much, Duarte. Thank you so much for your talk. And
My pleasure.
if you guys have more questions, you can contact Duarte later.
All right. Thanks a lot, guys.
Thank you.